Hey there, and welcome. Have you ever been in an airport, looked out the window at a jumbo jet, and just thought to yourself, how in the world does that thing fly? I mean, we're talking about a massive piece of metal weighing hundreds of thousands of pounds. Well, today, we are going to unravel that exact mystery.
Right? This is the big question. It just doesn't seem possible. Air feels like, well, like nothing, but somehow it has enough muscle to hoist a flying fortress into the sky. The answer isn't magic. It's actually this incredible piece of physics that's happening all around us, all the time, from a curving baseball to, yes, the wings of a plane.
Okay, so first things first, let's talk about what I'm calling the squeeze and speed rule. You see, to get how lift works, we have to start with a really basic rule about how fluids behave when they're moving. And yeah, you heard me right, air is a fluid.
So, I want you to picture a perfectly calm, smooth river. Every little particle of water is just following the one right in front of it, making these beautiful parallel paths called streamlines. That's streamline flow. It's the complete opposite of, chaotic whitewater rapids where everything's churning. For our explanation to really click, we've got to think about air moving in this nice, orderly way.
Now look at these lines, the streamlines. Think of them like lanes on a highway for air particles. And notice what happens when the path gets a little narrower. The lines get all squeezed together. This bunching up is a huge clue. It's telling us that the air moving through that squeezed section has seriously picked up some speed.
And that's our first big rule right there. It's really just common sense when you think about it. Imagine a huge crowd of people leaving a stadium through a wide hall, and then they all have to funnel through a single narrow doorway. What happens? Everybody has to speed up, right? To get the same number of people through that tiny space. Well, air does the exact same thing. Squeeze it, and it goes faster. Simple as that.
Okay, so we've got piece number one of our puzzle. Squeezing air makes it speed up. Now, let's bring in the hero of our story, a brilliant Swiss physicist from way back in the 1700s named Daniel Bernoulli. He had this amazing insight about the connection between how fast a fluid is moving and the pressure it creates.
Bernoulli's principle is really all about a trade-off. It's a form of the law of conservation of energy. It basically says that for any fluid that's moving, its total energy has to stay the same. So that means if one part of its energy goes up, another part has to come down to keep everything perfectly balanced, kind of like a seesaw.
And here it is. This is the trade-off that makes flight possible. Get ready for it. When a fluid's speed goes up, the pressure it exerts goes down. This is the secret sauce. Faster-moving air pushes less. Let's just let that sink in for a second. Higher speed means lower pressure. That's the key to everything.
Now, here's the formal scientific way of saying it. I know it looks a little complicated, but all it's really saying is that the total energy, which is a mix of its pressure, its energy from pure speed, and its energy from its height, that whole sum always stays the same. For something like an airplane wing, the change in height is super tiny, so we can basically ignore that part and focus completely on that amazing trade-off between speed and pressure.
All right, we've got our two golden rules. Squeeze air, and it speeds up. Speed up the air, and its pressure drops. So now, let's put these two ideas together and finally solve the mystery of flight. But wait, before we get to that massive 747, let's look at a much simpler example you've probably seen 1,000 times. How does a pitcher make a baseball curve like it's defying gravity? Believe it or not, it's the exact same principle at work. Okay, look at the first image, the ball that isn't spinning. See how the air flows perfectly around it? The speed is the same on the top and the bottom. So, no difference in pressure, no curve. But now look at this spinning ball. It's actually dragging a thin layer of air around with it. On top, that spin is going with the airflow, so the air on top is moving faster. On the bottom, the spin is going against the airflow, which slows it down. So we have faster air on top and slower air on the bottom. Now, what do we just learn about speed and pressure?
You got it. It means we get a pressure difference. That super fast air on top creates a zone of low pressure, and the slower air on the bottom creates a zone of high pressure. And that high pressure from below literally pushes the ball upwards, making it curve. There's a name for this. It's called the Magnus effect.
And this brings us right back to the airplane. Because an airplane wing, or an aerofoil as it's called, is basically a genius invention designed to do exactly what that spinning ball does, but without ever having to spin at all. It's all about that clever shape.
Let's just walk through it step by step. 1. That curved shape on top of the wing means the air going over it has to travel a longer distance than the air going flat along the bottom. 2.
Since the air that's split at the front has to meet up at the back at the same time, the air on that longer, curved path has no choice but to move faster to keep up. 3. And here comes our hero Bernoulli. That faster air on top creates a zone of lower pressure. And finally 4, the slower air underneath is now at a higher pressure and it pushes the wing up. That upward push is lift. And that, my friends, is how you get a 500,000-pound airplane to literally climb into the sky. Amazing.
So you can see this principle is just incredibly powerful. But it's important to realize that it works best in a sort of perfect, ideal world. So let's take a quick look at the fine print.
Yeah, as the source material points out, the pure, clean version of Bernoulli's equation assumes a perfect scenario. The airflow is smooth and steady, not all choppy and turbulent. It assumes the air's density doesn't really change, and that there's no internal friction or stickiness in the air. Now, of course, the real world is a bit messier than that, but for understanding the fundamental reason a plane flies, this principle absolutely nails it.
So the next time you see a jet soaring overhead, you'll know the secret. It's not just about raw engine power pushing it forward. It's about this beautiful, invisible dance of speed and pressure happening over and under its wings. Which leaves us with one final thought. If fast-moving fluid creates low pressure, could that also be the reason why the shower curtain always seems to attack you when you turn on the water? Something to think about. Thanks for digging into this with me today.